Okay, the title is on the screen, so let's welcome Tay Rong. Okay.
Thank you. Good afternoon. I'm Tay Rong Chang from National Cheng University. First one, I thank organizers' invitation for giving me this opportunity to share our recent new understanding into a topological system, especially on the bulk boundary correspondence, this fundamental concept in topological phase. And to avoid today's topic too diverse, I'll focus on quantum spin Hall insulator in today's talk. So I apologize that this talk is related to the topology, nothing to do with the quantum today. Okay, before starting today's topic, let me briefly introduce the basic properties of topological phase. And quantum anomalous insulator is a prime example. Topological phase in material can be defined through a series math known as topological invariant number, which can be used to identify the topological phase transition of the system. So phenomenologically, topological material have a bulk gap, while its boundary state is gapless. This unique property that distinct from normal band insulator comes from the concept of bulk boundary correspondence in the topological band theory. So in simpler terms, non-zero topological invariant number guarantee number of gapless topological boundary states. So in this example, our topological invariant number, here is the Chern number, C equal 1. So you can see there is the gapless topological boundary state that connect variance and the conduction band within the bulk gap region. So in this case, no matter what you tune the value of the Fermi energy within the bulk gap region, you always pass through the gapless topological boundary state. And this behavior is the hallmark of topological phase. And most importantly, this gapless boundary state is experimental observable. So let's see their relationship. Based on experimental observation, we know that the anomalous conductivity sigma xy here is proportional to e squared of h and an integer number n. And by using the Cooper formula, we know that the whole conductivity is derived from the geometrical phase of the valence electron, and here is the Berry phase, and is proportional to an integer number c we call the Chern number, which is the topological invariant number. Therefore, according to the bulk boundary correspondence, number of Chern number guarantee number of gapless boundary state on the edge of the system. So let's back to this example once again. The topological invariant number, Chern number, here is 1. So we see only one gapless boundary state in the bulk gap region. So if Chern number is 2, we'll see 2 gapless boundary states. So, the brief summary of this part, topological invariant number and the gapless topological boundary state are 2 most important ingredients of topological phase. Topological invariant number is the bulk property, and gapless topological boundary state is the edge property. So the relation between of them is through the bulk boundary correspondence. So this is the key of the topological phase. And besides the quantum anomalous insulator, another type of topological phase, symmetry-cooperated or so-called symmetry-protected topological state, has attracted attention in the past 2 decades. For example, quantum spin Hall insulator or 2-dimensional topological insulator. The symmetry, in this case, the gapless topological boundary state in symmetry-protected topological state is protected by a specific symmetry. For example, its gapless boundary state protected by the time reversal symmetry. The symmetry-protected topological state is quite robust. It does not open a gap or destroy it by any external perturbations. However, just like Superman's weakness is kryptonite, if the symmetry condition in this type of topological state is removed, this gapless boundary state will be easily destroyed. So let's see this example. We see a gap on the original topological boundary state when we include a Zeeman exchange field in the Hamiltonian to break the time reversal symmetry. So in this case, you can tune the value of the Fermi energy in the Ball gap region without pass through any topological boundary states. So in this situation, we can ask an RBS question. Because the boundary state is no longer connect valence and the conduction band, is this system topologically trivial? If we follow the typical process, we follow the band theory, band structure, or the symmetry analysis point of view, yes, it is topologically trivial. However, if we adopt another point of view, we call the feature spectrum topology, we'll find its hidden topological phase. So this is the outline of today's talk. I have introduced our motivation, and let me recall our central question once again. If we include a symmetry-breaking term in the Hamiltonian, if the boundary state no longer connect valence and the conduction band, is this system topologically trivial? To answer this question, I'll introduce the feature spectrum topology. I'll show you how we define the topological invariant number and identify the topological boundary state in the feature spectrum based on the Hamiltonian model. In addition, I'll also show you what is the feature energy duality. This is the core of today's talk. And in the end, we propose a multilayer, BI4, BR4, as a possible candidate to investigate the feature spectrum topology. Okay, so let me introduce the feature spectrum topology. The key of the feature spectrum topology is quite simple. At least for me, it's just like a basis transformation. In traditional quantum mechanics, we can solve the eigenvalue equation and then obtain the eigenvalue and the corresponding wave functions. And according to the previous study on the topological system, we know that the band topology mainly comes from the valence electron. And the valence electron in solid is characterized by an internal quantum degree of freedom. For example, the spin or the lattice symmetry, something like that. Therefore, we only need to focus on the feature that distinguish the internal quantum degree of freedom of the valence states. This is why we calculated the topological invariant number in the typical process from the valence band structures. Therefore, we can formulate our feature operator by projecting arbitrary quantum operator onto the occupied states. And this operation will partition the block wave function into distinct sectors, which is the eigenvalue of the feature operator we call the feature spectrum or the feature bands. So this panel is the typical result of the feature spectrum. And these lines are the feature eigenvalue. And these two areas, we call them sectors. Therefore, we can use the feature eigenstate of these sectors to define the topological invariant number and then identify the topological phase transitions. So let me show you some examples. We'll first introduce the typical process of studying the topological phase and then introduce the feature spectrum topology. This approach may help us to better understand the advantage of the feature spectrum. Okay, so let's start from the Hamiltonian model with the spin basis. And this model is a typical model to describe the quantum spin Hall insulator. And okay, so the first term in the Hamiltonian is the typical type-binding Harping term, and the second term is the intrinsic spin orbital coupling. So if we only consider these two terms, Hamiltonian model can be regarded as consisting of two independent Hall models with upside spins. Therefore, both the spin up and the spin down state are the eigenstate of the SZ spin Z operator. So SZ is conserved in the K-Malay model. For this reason, we can perfectly decompose the band structure